Hey, what's up guys? I'm going to show you a quick video on valence electrons, getting into Lewis structures, showing you some quick tips and tricks of how you can draw them more efficiently. So where we're going to want to start is we're going to want to start by looking at our periodic table. And from there, I'll give you guys some tips and strategies of how we can look at each of the different elements that are present there. So what we're looking for here is we want to look at a bunch of the different columns. We can see we have a bunch of different numbers above these columns. This is part of the reason that I love this periodic table. I think it's a little bit more straightforward in terms of explaining. The reason that I haven't highlighted any of the ones down here is because these are all known as the transition metals. And as far as we are concerned, when we're drawing out Lewis structures, transition metals are tough because they often present for us multiple charges. If you look specifically just at manganese here, you can see that manganese has the potential to have either a +2 or a +4 charge. So in terms of drawing its Lewis structure or predicting its charge, it becomes infinitely more difficult to do so. Now, one of the beautiful things about the periodic table and the way that it's organized is that each column represents its own certain charge. So if something's in a specific column, I can predict what charge it will have. If we look at this first column, column number 1 here, and we look at hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, all of them, every single one of them has a +1 charge. And so we know that without even having this special periodic table, if we see a hydrogen, lithium, sodium, etc., we know that it'll have a +1 charge. If we look down here at beryllium, we can see that all of those guys have a +2 charge. If we look at the column of boron, all of those guys are going to have a +3 charge. And where this starts to get a little hazy is in the +4 and -4 section. So once we get to a certain point, elements always want to have a full valence shell. The valence shell is the outer shell present on the atoms, and they always want to have a full valence shell. And generally speaking, that means they want to have 8 valence electrons, generally when we're looking at the periodic table. And so what the elements will do is they'll either give up or receive more electrons to fill up and get closer to 8 electrons. So if we just flash back briefly to what we did previously, a +1 charge would indicate that hydrogen, lithium, sodium, and everything below it would like to give up 1 of its electrons. Beryllium, magnesium, calcium, strontium would like to give up 2 of their electrons. Boron and everything below, 3 electrons. But when we get to this 4 stage, the question becomes, is it easier to give away 4 electrons or receive 4 electrons? And the reality is there's no difference. So we can't really know whether it's going to give up or receive 4 electrons. This is also part of the reason that carbon is the backbone for a lot of organic compounds, so a lot of living organisms, because carbon doesn't really want to give up or receive 4 of electrons. Rather, it would just like to share its 4 electrons that it has. As we get further, we now are looking at nitrogen. You can see nitrogen and everything below that has a -3 charge. Oxygen, everything below it has a -2. Fluorine's a -1. And then as we get to the noble gases, that section number 18, we can see that they don't have a charge. And the reason that they do not have a charge is because they have a full valence shell. In other words, that outermost shell has 8 electrons already. It doesn't want to give up, nor does it want to receive any more electrons. And so the reason that I show you these charges is A, to give you an idea of what charges you can expect. When I look at calcium and see it's in the second column, I don't need to look at this super handy table of ions right here. I don't need to look at that. I know it's in the second column, and so I can predict that it'll have a +2 charge. Where this becomes beneficial is we can also start to predict the number of valence electrons. So I'm going to do the number of valence electrons in black here. If hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium all want to give up or have a +1 charge, if they want to give up 1 electron or have a +1 charge, what that tells us is that they have 1 valence electron. We can move on to the next beryllium here and see that those have 2 valence electrons. If you remember back in grade 10 drawing Bohr diagrams, if I were to draw the Bohr diagram of beryllium, it would look something like this. We'd have that inner shell with 2 electrons, and then our next shell would also have 2 electrons. Well, what beryllium would like to do is just simply get rid of these 2 outermost electrons. It'd like to get rid of this one here and this one here. And what that'll allow it to do is have a full valence shell. As we keep moving, we can see this +3, they have 3 valence electrons. These guys have 4. Now, where it gets a little bit confusing was with nitrogen. So we have a -3 charge. In other words, it wants to receive 3 electrons to get up to 8 total electrons. So what it means right now is that it has 5 valence electrons on its outer shell right now. And if it receives 3 more and gains a -3 charge, it will be up to 8. So we say that nitrogen has 5 valence electrons. Oxygen and everything below it has 6. Fluorine and everything below it has 7. Helium and everything below it has 8. And what we can tell from the noble gases is they do not have a charge. They don't want to give up or receive any electrons. They are also very, very stable elements, which means they don't want to react. And so the goal of every single element is to get to that point where they have a full valence shell and they don't want to react anymore. That is ultimately their goal of what they want to achieve. If we start looking at valence electrons then, we want to be able to draw those as what's called a Lewis dot diagram. And to draw something as a Lewis dot diagram, all we're going to draw is, instead of doing the Bohr diagrams where we show each individual little element, we only want to do the valence electrons. That's the only thing we want to represent. So the first compound that I'm going to pick here is I'm going to just pick hydrogen. If I'm doing the Lewis dot diagram for hydrogen, ooh, that was sloppy. If I do the Lewis dot diagram for hydrogen, what I'll want to do is put the element symbol somewhere, and then I'll want to represent how many valence electrons it has. So if I go back to my periodic table, hydrogen's in that first column, so it only has 1 valence electron. And we could just draw it like this. Now, the beautiful thing is hydrogen and everything below it will have the exact same Lewis structure. So I could choose francium here, which has a ton of protons and electrons. But as far as the valence electrons are concerned, and the Lewis dot diagram is concerned, it looks like that. It looks the exact same. Again, we're only drawing the valence electrons, and as a result, we're only showing that 1 dot. Now, some of you might be wondering, does it matter where you put that dot? It does not. I'll show you and tell you in a second here when it does matter. Let's do an example where it in fact does matter. Let's do oxygen. That seems to be a really common element that exists in our universe. So if we do oxygen, again, I'm going to want to start with the same thing. I'm going to want to do my element symbol, which is just O, and draw that. I'll then go to my periodic table and say, okay, what column is this in? It's in column number 16 here on my periodic table. I know that it has 6 valence electrons, and it would like to gain 2 more to get up to that 8 valence electrons. And so what I'll start doing is I'll start drawing my 6 electrons. The way you want to draw your electrons is you always want to start by drawing your electrons opposite to one another. So there's 1, 2 valence electrons, 3 valence electrons, 4 valence electrons. So I've got my 4 sides, I guess, of oxygen drawn out with valence electrons. I still need 2 more. This is where we start to create something called lone pairs of electrons. So I'm going to draw another electron right beside this first one up top here. I'm going to draw another electron down here. And so that is what the Lewis dot diagram of oxygen would look like. Again, you want to start by putting singular electrons on all 4 sides or 4 corners of it. And then after that, if you need to add more in, you start pairing them up in what's called a lone pair. So this guy here is called a lone pair. Where this will become really prevalent for us is a lone pair is considered like a bond. Anytime you have a bond between 2 things, it means that there's 2 electrons present in that location. So if we have a lone pair of electrons, generally speaking, it's really stable. It doesn't want to react or form a bond somewhere. But these 2 singular electrons, this guy here and this guy here, those ones are going to be really unstable and want to form bonds. And that's why when we start seeing something like water, for example, so we have hydrogen up top. It has 1 lone electron, 1 singular electron. That is going to want to form a bond somewhere. And if we look at the Lewis dot diagrams of water, and we draw the oxygen and we draw our two hydrogens, H2O is water, what we'll start to see is that these two electrons here are going to bond up and join together. And this is what the structure of H2O ends up looking like. So that's a quick tutorial on how to count valence electrons based on the periodic table, also how to draw Lewis diagrams, and then what we did as well is we formed bonds within our Lewis structure as well. Hope that was helpful. Let me know if you have any questions at all. I'd love to help you out.